some time.
Let's start, ma'am. Otherwise, they will make a habit of joining late.
Okay. Okay, so students, today you are going to perform experiment number 2. Experiment number 2, that is generation of frequency modulated signal, FM signal, and calculation of modulation index. Calculation of modulation index. Modulation index. And number 2, demodulation of FM signal. Demodulation of FM signal using PLL. In the trainer kit, you are using the PLL. Using PLL. Okay, so why PLL? Because in the trainer kit, you are using PLL. However, when you do it in the octave, you will be using some other logic for demodulation. But on the trainer kit, demodulation is done by PLL. You are already aware of it. Phase locked looped IC. Phase locked loop. Phase locked loop. IC. It is an IC. So basically, we are going to study FM today. We have already completed the analog, your amplitude modulation, SSB-SC, DSB-SC, all the 3 last class. Already it is completed both on the trainer kit as well as on the octave. So in similar way, today again, the next experiment is generation of FM signal and calculation of modulation index, and demodulation using FM, demodulation of FM using PLL. So in this again, I'll just give you some introduction about this FM, and then you will see the video demonstration, and then we will go to the octave programming. So FM, we are already aware about FM. We have done it in ACT. FM is nothing but frequency modulation. Frequency modulation. So in frequency modulation, what is happening? Frequency modulation is a technique in which the frequency of the carrier signal is changing with respect to the amplitudes of the message signal. So that means in frequency modulated signal, our information signal is getting transmitted over the amplitude, over the frequency variations of the carrier signal. So if you see this diagram in a simpler way, just refreshing what you have done. So suppose this is your message, low frequency message signal, empty, and this is the high frequency carrier signal, high frequency carrier signal. So now what is happening in frequency modulation? In frequency modulation, as the definition says, the frequency of the carrier signal will be changing with respect to the amplitudes of the message signal. So this, suppose the peak amplitude of message signal is AM here, and peak amplitude of carrier signal is AC. And now we are going to draw the third waveform, which is our FM signal waveform. So in frequency modulation, what is happening? Frequency of the carrier signal. So suppose the equation of carrier is represented as, say, AC cos of 2 pi FCT. And although I have drawn the sinusoidal waveform, so suppose in my equation we write, or you can write it as sine also according to the diagram, since the diagram is a sine wave. So suppose it is AC sine 2 pi FCT, and MT is represented as AM sine 2 pi FMT. So these are the two sinusoidal signal with frequency of carrier much greater than the frequency of the message signal. So now in the frequency modulation, what has happened? The frequency of carrier signal. Frequency means which parameter? The time period. Isn't it? Frequency FC is equal to 1 by TC. So the time period of the carrier signal, which is initially constant. At present, the time period is constant. Once frequency modulation takes place, means once we give message signal and carrier signal, when message signal from the microphone and the carrier signal from an oscillator, when they are applied to FM modulator circuit, FM modulator. What are the two types of FM modulators? One is called as direct method, another is called as indirect method. In the direct method frequency modulator, you are using a Hartley oscillator and all that you have already studied. So one method of where is the screen gone? Just a minute. No. One method of, let me take a new screen now. Just clear all. Just a minute, let me just see where did the screen go. Okay, now it is okay. So let me make the diagram again. So we were discussing about FM, isn't it? FM waveform. Just quickly I will make. So in FM waveform, suppose now let me draw the cosine waveform. So this is our message signal with peak amplitude as AM, and this is our carrier signal AC cos 2 pi FCT. Both are cosine waveform. So I'm drawing cosine waveform now. Whose peak amplitude is AC. And now we are drawing the FM waveform. So in frequency modulation, SFM of T, y-axis, and x-axis T. So in frequency modulation, frequency of carrier signal is changing according to the amplitudes of the message signals. You can see initially peak amplitude of message signal is AM here. After this peak amplitude, the amplitude of message signal is reducing like this. And at here minus AM, it is the minimum amplitude. Again, the amplitude of message signal is increasing. So this is how the amplitude of message signal is changing. And accordingly, the frequency of carrier signal is also changing in frequency modulation. So for higher amplitudes, the frequency of the carrier signal will be more like this. And as the amplitude of the message signal is decreasing, again the frequency of the carrier signal will be decreasing like this. And at the minimum amplitude of the message signal, the frequency is minimum. Again, as the amplitude of message signal is increasing, the frequency of carrier signal will be increasing like this here. And it will be maximum at the peak amplitude. And again, it is going to, and this is going to continue. So you can see initially the time frequency means time period, frequency of carrier means 1 by Tc. So initially before modulation takes place, the time period of the carrier signal is constant. After frequency modulation has taken place, the frequency of the carrier has increased for the increase in the amplitude of message signal, and frequency of carrier signal has decreased for the decrease in the amplitude of message signal. That means in frequency modulation, the information signal is being carried in the frequency variations of the carrier signal. Amplitude of the carrier signal remains constant in frequency modulation. In amplitude modulation, what was happening? In amplitude modulation, the amplitude of the carrier signal were increasing and decreasing according to the amplitude of the carrier signal, message signal. This is the AM signal waveform. In the if same message signal and same carrier signal you're performing amplitude modulation, then the amplitude modulated signal waveform looks like this, in which the amplitude of the carrier signal has increased and decreased according to amplitude of the message signal. Whereas in frequency modulation, the same message signal, same carrier signal, if you're performing frequency modulation, then in frequency modulation, the frequency of the carrier signal have increased and decreased according to the amplitudes of the message signal. For more amplitude, more frequency means number of cycles are more. For less frequency means number of cycles are less. Again, for more frequency means number of cycles are more. Lesser frequency means lesser amplitude means, or lesser frequency means the number of cycles are more. So therefore, this is how the frequency modulated waveform is going to look. So in once you perform frequency modulation, the hello signal or message signal is now in the frequency variations of the carrier signal. Amplitude remains constant. So this is the frequency modulation concept. Now we'll just go through some mathematical equations of frequency modulated signal. So mathematically, how do we represent frequency modulated signal? So there are three equations we have done in the class. The first equation is S of t for Fm is nothing but AC into cos of 2 pi FCT plus 2 pi KF integration 0 to t mt dt. So this is the most basic equation of the FM which you have already derived in the class. So the FM signal which we have generated is mathematically expressed as AC cos of 2 pi FCT plus 2 pi KF integration MTDT, where KF is called as the frequency sensitivity of modulator. Frequency sensitivity of modulator, and its unit is in hertz per volt. Hertz per volt. All this is using the derivation, all the equation. Second form of expression of your FM is your S of t for FM for single tone message signal is expressed as AC cos of 2 pi FCT plus beta sine 2 pi FMT. Beta sine 2 pi FMT, where beta is called as the modulation index of FM. Modulation index of FM signal. And the formula to calculate beta, where beta is nothing but it is a ratio of frequency deviation to the frequency present in the message signal or the message frequency. So where here del f is called as the frequency deviation of FM, and FM is nothing but your message frequency. All this you get from the derivation. All that derivation I'm not doing here. So therefore this one, that means in this equation, in equation number 1, if we replace MT as single tone expression, MT, if we take MT as AM cos 2 pi FMT, single tone means our message signal is containing only one frequency component. So if we replace the message signal MT with a single frequency component message signal in the form of AM cos 2 pi FMT, that means it is called a single tone message signal. And if we do the derivation, integration of AM cos 2 pi FMT, if we do, then when we integrate AM cos 2 pi FMT, we will find that you will get some expressions in the form of KF into AM divided by FM. This is what you get after integration in the derivation. So KF into AM is nothing but your frequency deviation, and FM is the message frequency, which gives rise to this expression del F by FM, which is called as the modulation index beta of the FM signal. So this is the second expression of the FM. The third expression that we are aware of is using the Bessel function. Using Bessel function, again we have another expression of FM. So S of t for FM using Bessel function is nothing but AC into summation n equal to minus into plus infinity Jn beta into cos of 2 pi Fc plus n FM of t. So this is the third equation using Bessel function. What is the application of this equation? This equation of Bessel function is used for the frequency domain analysis of FM, isn't it? And to plot the frequency spectrum. The previous equation, that is AC cos of 2 pi FCT plus beta sine 2 pi FMT, this equation cannot be used for frequency domain analysis, because when for frequency domain, to get a frequency domain S of F, is to get a equation in F domain, we have to apply Fourier transform to this expression. And if you see this expression, if you expand this expression, this is in the form of cos A plus B. So it becomes cos A into cos B plus sine minus sine A into sine B. So this becomes cos 2 pi FCT into cos of beta sine 2 pi FMT. So the expression will come in the form of cos of sine. That means you will, if you use this equation to apply Fourier transform, then what is happening? We are expanding this equation, and we will find that we will get the expression in the form of cos of sine and sine of sine. You will get something like this after expansion using cos A plus B formula. So there is no formula for Fourier transform of cos of sine and Fourier transform of sine, and this cannot be further expanded using trigonometric formula. You cannot use, there is no trigonometric formula available for the expansion of cos of sine and sine of sine in this previous expression when we do this expansion. So therefore we have to take help of the Bessel function. We have to express second equation using Bessel function, and we get using second equation and Bessel function, we get this third equation. This third equation you can see is of this form. And when we apply Fourier transform this to this expression, then you simply have to use the Fourier transform of a cos signal, cos formula, which is nothing but 1 by 2 del of f minus f1 plus del of f plus f1. So this is because this is simply a cos signal now. So applying Fourier transform of cos formula, we can expand this equation and we get the frequency domain equation. So that is the importance of the third equation. So these are the three mathematical ways by which the frequency modulated signal can be represented. So we have seen now, we have understood that what is FM. FM in frequency modulation, frequency of the carrier signal is increasing and decreasing according to the increasing and decreasing amplitudes of the message signal. The amplitude of carrier signal remains constant. That means in frequency modulation, our information signal is being carried in the frequency of the carrier signal. Amplitude remains constant. The frequencies of the carrier signal have changed in proportion to the amplitudes of the message signal. So in frequency modulated signal, the frequencies of the carrier signal are now carrying our message signal in the FM waveform. These are the three mathematical ways by which we can represent the FM signal. The second equation is more useful because the second equation is giving us the formula of the modulation index beta equal to del f by fm. Del f is called as the frequency deviation of fm, and fm is the frequency of the message signal. Then what is the significance of frequency deviation? What is del f? Which is the frequency deviation. Frequency deviation means, you see here in this, but you see this waveform. If you see this waveform, in this waveform there are two frequencies now. So here you see, so we have basically we have three frequencies. FM is the frequency of the message signal, FC is the frequency of the carrier signal, and once frequency modulation has taken place, we get a new frequency which is called as FIT. FIT is the instantaneous frequency of the FM signal. FIT is the instantaneous frequency of FM. Instantaneous frequency of FM. So we have three frequencies in this waveform: frequency of message, frequency of carrier, and the instantaneous frequency of FM, which is FIT. That means, so from where this FIT has come? Because FIT has come because after frequency modulation has taken place, the frequency of the carrier signal, which was FC, has now changed with respect to message signal MT, isn't it? By definition of frequency modulation, we know that the frequency of carrier signal FC has increased and decreased with respect to the amplitudes present in the message signal. So that means an instantaneous message signal MT has changed the frequencies of the carrier signal, which is FC. So the new frequency of the FM signal is no longer constant. The frequency of the frequency modulated signal is no longer constant. It has now become a proportion to the which signal? Message signal. So therefore, we cannot write Fi only. We have to write it as FIT, because FIT is proportional to the amplitudes of the message signal. So therefore, the frequency of the FM signal after frequency modulation has taken place, the output frequency of FM is referred to as instantaneous frequency, which is proportional to the voltage of the message signal, that is message signal itself. So this is your instantaneous frequency. Now what is frequency deviation? From where this del f has come? So therefore the difference between the instantaneous frequency and the carrier frequency, this difference, the magnitude, modulus, positive value, frequencies are always positive. So therefore the difference between the instantaneous frequency and the carrier frequency, that is called as frequency deviation. That means after frequency modulation has taken place, what is the amount of change or what is the amount of deviation in the frequency of carrier signal which has occurred with respect to the original carrier frequency. So how much amount of FIT has changed with respect to FC, that is called as frequency deviation. So frequency deviation can have two formula. One is that it is the difference between the instantaneous frequency and the carrier frequency. Another formula, according to the derivation of equation 2, according to derivation of equation 2, according to this derivation, we are finding that the another formula for frequency deviation is kf into am when we derive the equation. So there are two formula for frequency deviation. One is kf into am according to the derivation, and another is according to the concept. It is the difference between the instantaneous frequency and the carrier frequency, because after frequency modulation has taken place, the frequency of carrier signal has changed with respect to message signal. That is the definition. So the new frequency of the fm is referred to as fit, and the old frequency of the carrier is referred to as fc. So what is the change between fit and fc? That is called as frequency deviation. So this is the concept of frequency deviation in fm, and all the three equations we have already now discussed. And in the experiment, you have to calculate the modulation index. So the formula for calculating the modulation index is nothing but del f by fm. That is it is the normal equation in the derivation, that beta modulation index beta can be found by taking the ratio of the frequency deviation to message frequency. So in the lab, when the trainer kit, when we are finding out the modulation index, obviously we are not using that the second formula. Del f cannot be found by kf into am formula in the lab, because you are observing the waveform on the CRO, and therefore on the CRO there is no question of kf constant, and using kf, finding out kf and then multiplying it with am. That formula cannot be used to find del f. So del f is found by the first formula, this formula, difference between the instantaneous frequency and the carrier frequency. That means difference between the fm frequency and the carrier frequency for one cycle you will calculate, and that difference will give you the frequency deviation, which will be used for the formula of the modulation index in the lab. Okay, so these are the different types of equations representing fm. Then there are two types of FM you have learned in the class. What are the two types of FM? One is called as wide band FM, another is called as narrow band FM. In wide band FM, your modulation index beta is much greater than 1. In narrow band FM, modulation index beta is much less than 1. And they both have different type of mathematical equations. Those we are not going into details because they are not relevant in the lab. Just you should remember, just in case, just you should know what is wide band, what is narrow band. Now wide band FM modulation index beta is much greater than 1. Narrow band FM modulation index beta is much less than 1. Then what are the methods of modulation and demodulation? FM modulators. FM modulators. Two types of FM modulators are there. One is called as direct method, another is called as the indirect method or the Armstrong method. Indirect method or Armstrong FM transmitter, which you have already done. And similarly, so in the direct method, you are directly generating the wide band FM using a Hartley oscillator. In the theory you have already learned. And the indirect method, you first generate in the indirect method, you first generate narrow band FM. You first generate narrow band FM at lower frequency, and then using frequency multipliers, you then increase the frequency and then convert narrow band FM into wide band FM. So what is the need of the indirect method? Why we are using this method? Why should we first generate narrow band at low frequency and then increase it by wide band? Because in the first method, in the direct method, when we are trying to generate wide band FM, in that we need a very high carrier frequency, and very high carrier frequency sometimes becomes unstable. And if the carrier frequency becomes unstable, if the carrier frequency itself becomes to is changing, suppose this carrier frequency fc changes on its own, then obviously it is a very adverse effect on fm, because the carrier change in the carrier frequency should ideally happen according to the amplitudes of the message signal in fm, because that is now carrying the message signal. But if the change in carrier frequency is occurring on its own without the effect of message, then that becomes that will bring ambiguity in the fm output. So it will be not be clear whether this change has occurred due to the change in the amplitude of message, or whether the change has occurred due to the change in the carrier frequency itself. So if we are using very high frequency carrier signal in the generation and trying to generate wideband FM, then this instability in carrier frequency takes place, and to manage it we need some negative feedback circuits also in them, which makes the circuit more complex. So therefore in the second method, in the indirect method, what is done is that we are first generating narrow band FM at lower frequency to, and gradually we are increasing the frequency of narrow band FM to wideband FM by applying narrow band through frequency multiplier circuits. So first we generate narrow band FM and then apply it to frequency multiplier to convert it into wideband FM. So gradual increase in frequency is taking place in the indirect method, and therefore frequency stability is maintained. So two FM modulators, direct method and indirect method. Then how are we demodulating FM signals? FM demodulators are of three common types. One is called as your frequency discriminator. Frequency discriminator. Frequency discriminator. Second is your PLL as FM detector. PLL as FM detector. And third is your zero crossing detector. Zero crossing detector. Okay. So these are the three common ways by which we are demodulating. Demodulating means recovering message signal from FM. Recovering message signal from FM signal. FM signal. So now we should remember that in FM, where is the message signal? In FM, message signal is in the frequency variations, isn't it? In the frequency variations, message signal is present. This is our FM signal. We are receiving this signal. From this signal, we should get back our message signal. This signal we should recover. Message signal should be separated from this signal. Where is this message signal in FM? It is here. In the time, in this frequency variations, this message signal is there. Here is the message signal. We have to extract this message signal from these zero crossings, from these points, and get back our message signal. We have to recover message signal from the this frequency variations. We have to recover message signal. So there are three ways by which we can recover this message signal from the frequency variations. One is called as frequency discriminator, another is called as PLL as FM detector, is phase lock looped IC, and third is called as a zero crossing detector. So in the lab, in the trainer kit that we have, you are using PLL as FM detector, where there is a PLL IC 565, and you have already seen in the ACT, in the block diagram of PLL IC consists of it consists of a multiplier, isn't it, and a loop filter with a VCO voltage controlled oscillator in the feedback path. So this is the internal block diagram of PLL IC 565. Input to the PLL IC is your FM signal. So FM signal is applied to a multiplier which is working as a phase detector followed by a loop filter, and the output is fed back through another circuit which is called as VCO voltage controlled oscillator, which is again generating a type of FM signal only. So these are very vast mathematical analysis which I'm not going to do here. So you have to analyze S of t and R of t and generate some equation E of t, which is called error signal, which is applied to the loop filter. Output of loop filter will be your output V0 of t. So basically V0 of t from PLL is nothing but, you will, after you do the derivation, you will get the equation comes out to be Kf by Kv into Mt. So output V0t from this PLL IC is nothing but proportional to the message signal with a scaling factor of Kf by Kv. Kf is the frequency sensitivity of FM and Kv is the frequency sensitivity of the VCO. So as I told you, the output of VCO and the input FM both are given to this phase detector, which is a multiplier working as a phase detector. So equation of ST and equation of RT, both these equations are multiplied here. And once they are multiplied, that multiplied output is applied to a loop filter. Loop filter is a low pass filter. So the low frequency components present in the equation is allowed to pass through it. And in that one cycle, that equation, that low loop filter output is nothing but your error signal E of t. And in this concept that the amount of voltage V of t, which is, so I'm just giving you here. So in PLL, what is, because PLL is there in the PLL as FM detector, just in short, I'm just giving you an idea. So in PLL as FM detector, this is the block diagram. There is a multiplier, there is a loop filter, and this is a VCO, voltage controlled oscillator. Okay, and this is the output V0t, which is approximately equal to KF by KV into MT as per the equation. Input is our FM signal, and an output from the VCO is denoted as R of t. So now what is VCO? VCO is called voltage controlled oscillator. Voltage controlled oscillator. So that means the output frequency, as the name suggests, voltage controlled oscillator is a circuit whose output frequency means oscillator means it will produce oscillations. So therefore, the frequency of these oscillations are proportional to the voltage applied across it. According to the name, you can say it is voltage control oscillator. The frequencies of this the oscillator output, or the signal frequency of this oscillator, will depend on the voltage applied across it. So what does this mean? This means that the voltage controlled oscillator has the ability to produce FM signal from itself, because the in frequency modulation, the very concept of FM is that in frequency modulation, what is happening? In frequency modulation, if this is your message signal and this is your carrier signal, then in frequency modulation, the frequency of carrier signal has increased and decreased according to which signal? According to the message signal, isn't it? That means the frequency of carrier signal has changed according to message voltage, and that has given us FM signal. Similar process is taking place in VCO. In VCO also, it is an oscillator. It is generating some signal waveform here, whose frequency is proportional to the voltage applied across it, because it is a voltage controlled oscillator. So the output voltage V0t is nothing but is fed as an input to this voltage control oscillator. So this voltage V of t is controlling the frequency of this output oscillator, which is nothing but represented. So that means the equation of VCO, implying all this concept implies that the equation of VCO is nothing but same as the equation of FM, because the very working of VCO says that the output frequency of this oscillator is nothing but controlled with the input voltage, which is in similar lines with that of FM. In FM also, the output frequency of the carrier signal is changing with respect to the message voltage. Similarly, the output frequency of VCO is changing with respect to VT voltage. So the equation of RT from VCO will have similar format as that of the FM equation, and both these equations are then given to a multiplier for multiplication analysis will take place. Now in this particular phase lock loop, what is the concept? So FM equation, if we know, it is AC cos of off. It's already getting late. So quickly just PLL, because it is there in your trainer kit. So therefore what we are discussing, so equation, I'm writing the equation directly now. So this is the diagram. That this is multiplier as phase detector and loop filter, and this is our VCO, and output is V0 of t, and this is the error signal E of t. So this is FM input, and this is R of t. Okay, so just now we have discussed the concept. So now, and so therefore multiplier is working as a phase detector. Multiplier is working as phase detector. Phase detector. Okay. So this is the internal block diagram of IC 565 PLL. Inside PLL IC, a multiplier as phase detector, a loop filter as low pass filter. Loop filter is a low pass filter, and a voltage control oscillator. These are present inside the IC 565 PLL IC. So now what is the concept here is that we know that the FM equation is equal to AC into cos of 2 pi FCT plus 2 pi KF integration 0 to T MT dt. This is the equation of FM. So this is nothing but this is nothing but the phase phi t of the cos equation, because any cos equation is nothing but cos omega t plus phi, isn't it? Cos omega, any analog signal you write a cos omega t plus phi. So here phi is not a constant, it is a time varying phi because it is in the form of a signal mt. So this is our phi t. This is the phi t of the cos, phase of the cos, which is represented in FM. Similarly, the output of VCO, as I just now discussed, is will be another FM only, because the format of VCO, the principle of VCO is same as FM. The output frequency of this VCO is controlled by the input voltage V of t. So the output equation of VCO RT is similar to that of FM. So we will write the equation of RT as AV into cos or sine, anything you can write, 2 pi FCT, your frequency is assumed to be same, into plus 2 pi kV integration 0 to t V of t dt, where V is the input of the VCO. So we have got two equations here. Again, in the second equation, this part of the RT equation is called as phase phi 2t. So this part, this for FM it is phi 1t, for F2 this is phi 2t. Now if you observe the equations, in the equation, where is our message signal? Our objective is to extract message signal. We have to recover this MT out of this FM. Isn't it? From this complete FM equation, we have to get only MT. So by concept, where is this MT in this equation? The MT is contained in the phase of the cosine waveform. The phase of the cosine waveform is carrying MT, isn't it? So therefore, this multiplier is working as a phase detector, and this is called as phase locked loop. So from this concept, we are using PLL phase locked loop for our demodulation, because you see this phase locked loop means why do we need to use phase here? Because from the mathematical concept we are understanding that the phase of the cosine waveform, that is phase phi 1t, is carrying the message signal. So by using PLL IC, which consists of multiplier, loop filter and VCO, we are able to extract the phase of the carrier signal. So if we are able to extract the phase of the carrier signal, we are able to extract the message signal, because message signal is carried in the phase of the carrier signal. So therefore, so there are two phases in this particular system. One is phi 1t for the input FM, which is carrying message signal. Another is phi 2t, which is V of t, which is output from the VCO. Both of these signals are multiplied here. That means output of the multiplier will be S of t into R of t, and you will get some equation, big equation here, because you are multiplying this complete equation is multiplied with this big equation. Both the big equations are multiplied, and the low frequency components present in that equation are allowed to pass through the loop filter. So the equation of loop filter will be low frequency component, and you will get the equation. When you do the derivation, you will get an equation in the form of phi of t equal to phi 1t minus of phi 2t after derivation. Phi 2t. This kind of equation you will get after derivation from the output of loop filter. This equation you will get from the output of loop filter. So therefore, that means you will get it in the form of like this. You will get it in the form of signal sine phi t. You will get something like this. You will get the equation as sine phi 1t. You will get like this: AC AV by 2 sine phi 1t minus phi 2t. This is the output of the loop filter that you will get. So this phi 1t minus phi 2t is called as phi et. This is called as phase error. Phase error. Okay, phase error. Okay. So now what is the concept of PLL? The concept is that the phase locked loop will always try to make phase error phi t zero. Phase error phi t should become zero. That is the approach of PLL. So how will PLL make phase phi error zero? It will make phase phi error 0 by making phi 2t equal to phi 1t. So if phi 2t, which is the phase of VCO, if the phase of VCO becomes equal to the phase of the your FM signal, then the difference between phi 1t and phi 2t will become 0. In that condition, the PLL will be called said to be in the locked state. During that time, PLL will be said to in the locked state. So that voltage V of t, you see phi 2t is what? Phi 2t is driven by voltage V of t. Phi 2t is driven by V of t, and V of t is the output voltage. V of t is the output voltage. So that voltage V of t, which has made phi 2t equal to phi 1t, that voltage is extracted as your message signal M of t. So that voltage corresponds to message signal M of t in the VCO, which is extracted from the PLL, and in that time phi t error will become equal to 0 and PLL will be in the lock state. And finally, with all the derivations, you will find that V of t output from the PLL becomes proportional to KF by KV, KF by KV into MT, and we will be able to extract message signal. So this is the concept of PLL, phase locked loop. We are using phase locked loop because the phase of the FM is carrying message signal, and this phase of FM is compared with the phase of the VCO, and all those processes are taking place in the PLL phase locked loop, and we are able to extract message signal from the phase of the input FM signal. So this is how you are doing. And quickly, I just want to discuss the frequency discriminator also, because this discriminator will be used in your octave. In the octave programming, we are not using PLL for the equations, because these equations are very complex. In the octave programming, you are using the concept of frequency discriminator. So what is frequency discriminator? You have already done all these things in the class in previous semester. In frequency discriminator is another way of extracting the message signal from FM. So what is happening here in frequency discriminator method? This method is also called as slope detector. Slope detector method. Slope detector. So quickly, what is the concept here is slope detector method to extract message signal is that you apply FM signal. FM is given to a frequency discriminator followed by an envelope detector. Followed by an envelope detector to extract the message signal. So what is frequency discriminator doing? Frequency discriminator is converting FM into AM. So frequency discriminator converts FM into AM. So that means the message signal which was currently and in the frequency variations, after passing through frequency discriminator, the message signal has now come onto the amplitude variations here. In FM input, message signal was here. Message signal is in the frequency variations in FM. Once we apply FM to a frequency discriminator circuit, this FM signal gets converted into AM signals. That means now the amplitude of the carrier signal is now carrying our message signal. So FM gets converted to AM using frequency discriminator, and once it gets converted to AM, we will then apply it to the envelope detector to extract the message signal. The working of envelope detector you already are aware of, and we will get back our message signal using this slope detector. So therefore, so what are the circuits which have the ability to convert FM to into AM? So there are two circuits which have the ability to convert FM. That means frequency variations converted to amplitude variations. One is called as differentiator as frequency discriminator. We can use a differentiator circuit to do this process. So what are the mathematical equations? V0 of the output of the differentiator is nothing but the differentiation of input, we already know. So now this is in time domain. If we apply Fourier transform and write it in F domain, then Fourier transform of V0 of t is nothing but V0 of F is equal to Fourier transform of d by dt of Vit. This is what we do, applying Fourier transform on both sides. So V0 of f becomes equal to 2 pi, that is j2 pi f. J2 pi f. This is the Fourier transform of d by dt of Vit. according to the differentiation property of Fourier transform, the Fourier transform of d by dt of Vit is j2 pi f. So you get this equation. So this is the relationship of differentiator in frequency domain. This is the relationship of differentiator in time domain. In time domain, the relationship of differentiator says that V out is equal to d by dt of Vit. In frequency domain, the relationship says that V0 of f is equal to j2 pi f. Both are the relationship of the same differentiator, one in time domain, another in frequency domain. So we are taking this frequency domain expression into consideration. So now if you see here, so therefore, and there is vi of f also here, because vi of t is there, so vi of f in the equation. So if you see the equation becomes v0 of f is equal to j 2 pi f into vi of f. This is the frequency domain equation. So now if I take the ratio of v0 of f divided by vi of f, if this, so this is nothing but j2 pi f, j2 pi f, isn't it? v0 by f upon vi of f. And so this is the ratio of output by input. So this is the transfer function h of f. This becomes h of f equal to j2 pi f. Okay, so therefore this is, now we got this new expression, h of f is the transfer function is equal to j2 pi f from this equation. Now if I take the magnitude of transfer function, magnitude, this pen is not working properly. So magnitude of transfer function if I write, then what is the magnitude is nothing but magnitude of this complex function j2 pi f. So the magnitude of this implies, using this property, you will get magnitude of transfer function h of f is nothing but 2 pi f, isn't it? Because the magnitude of a plus jb is nothing but under root a square plus b square. So here for j2 pi f, for this expression a is 0 and only jb is there. So that means you are going to do b square under root b square, isn't it? Under root b square. So under root b square means what? Under root 4 pi f square, 4 pi square f square. So under root of this is nothing but 2 pi f. So therefore the magnitude of transfer function becomes 2 pi f. So what is the implication of this expression? So this is an important expression which is useful to us. The magnitude of transfer function means magnitude, if you take the magnitude of any transfer function, it gives you the amplitude of that function, amplitude. So we find from this expression that amplitude is becoming proportional to the frequency. Amplitude has become proportional to the frequency. That means in a differentiator can be used to develop a relationship between amplitude and frequency. Magnitude of the transfer function of differentiator has become the function of the frequency present in the differentiator. So we have developed a relationship, a linear relationship between the amplitude and frequency in a differentiator. So what is the use of this? That means the use is that magnitude of transfer function becoming linearly proportional to the frequency. We have got a graph where you take the magnitude of transfer function in the y-axis, which is amplitude, and f on the x-axis, and we find that frequency and amplitude have a linear relationship. So when FM signal is applied to a differentiator, if we apply FM signal to a differentiator circuit, it will get converted into amplitude variations. Frequency variations will get converted to corresponding amplitude variations using a differentiator, because there is a linear relationship between frequency and amplitude. Frequency is the input, amplitude is the output. So when FM is applied to the input of a differentiator, it will get converted into corresponding amplitude variations. So therefore differentiator can be used as a frequency discriminator. Here instead of frequency discriminator, we will write here a differentiator. So FM will be allowed to pass through a differentiator. Differentiator will convert it into AM, which will then be applied to envelope detectors. So this differentiator is used in the octave. This differentiator function is used in the octave programming. Diff. The diff function will be used to extract the message signal. How did we extract? By converting FM into AM and then applying it to the low pass filter in the envelope detector, Butterworth filter. So this is about the your concept of FM which we have now discussed. Okay, so I think we are over with it. So I now request, any doubt, anybody? Have you all understood what we have discussed today? Anybody having any doubt? All of you are and have understood what we have discussed. FM.
Yes, ma'am.
Hmm.
Yes. Ma'am, could you just explain in a short manner, because I wasn't able to join in between. My network was not there.
Which part you want to know? Which part?
Ma'am, the first part, ma'am.
Initial, the initial FM part.
Yes, ma'am.
Okay. So initial FM part is the normal FM that you have studied in your theory FM. Is it? We learned FM. Today's experiment is FM. So we have discussed what is FM in frequency modulation. The frequency of the carrier signal is changing with respect to the amplitudes of the message signal. That is the definition of FM, isn't it? So this is, suppose this is your message signal with peak amplitude AM, and this is your carrier signal C of t with peak amplitude AC. So we have discussed that in frequency modulation, what will happen? In frequency modulation, the frequency of the carrier signal will increase and decrease according to the amplitude of the message signal. So this is our FM signal. So here you can see, here the frequency is high, here the frequency is less. Here the frequency is high, here the frequency is less. And how is this high and less frequency? According to the amplitudes of the message signal, the frequency has increased and decreased. So this is called as frequency modulation. So in frequency modulation, what is happening? That now the message signal is carried in the frequency variations of the carrier signal, amplitude is remaining constant. That is one concept. So this is the definition of FM. Now coming to the equations, there are three equations of FM we have discussed. Already I have written SFM of t is AC into cos of 2 pi FCT plus 2 pi KF integration MT dt. This is the in general equation of FM that we are already aware of, where MT is a any message signal MT. So this is the first way of expressing the FM signal. The second way of expressing FM is using single tone message signal. So for a single tone message signal, FM is expressed as AC cos of 2 pi FCT plus beta sine 2 pi FMT. Beta sine 2 pi FMT. So where beta is the modulation index of FM, which is expressed as del f by m. Del f is the frequency deviation of FM, and FM is the message frequency. So this beta, this expression of del f of FM and beta we get out of derivation. You replace MT. MT is replaced by AM cos of 2 pi FMT, single tone message signal. And when you integrate AM cos of 2 FMT, the integration of cos will give us sine. So you will get the expression in the form of del f by FM, means you will get KF into AM sine of 2 pi FMT divided by FM in the expression. So this KF into AM is called as del F, and in the denominator you have FM. So the ratio of del F by FM is called as beta, which is the modulation index, and cos has become sine because you are replacing, you are integrating here. When you are calculating the FM equation for single tone, so single tone equation of message is this AM cos 2 pi FMT. So when you integrate AM cos 2 pi FMT, cos will become sine. So therefore, second equation of FM is in the form of beta sine 2 pi FMT. For single tone message signal, beta is the modulation index. Then what is frequency deviation? We have developed, we have understood frequency deviation del f is nothing but the change in the frequency of the FM signal with respect to the carrier signal. So now in frequency modulation, what has happened? In frequency modulation, the frequency of the carrier signal has changed with respect to the message signal. That means in FM, after frequency modulation has taken place, the frequency of the carrier signal is no longer constant. The frequency of carrier signal has become proportional to the message signal. So therefore, the new frequency of FM after frequency modulation has taken place, that new frequency is denoted as FIT, which is called as instantaneous frequency, because it has now become a function of a voltage message signal. So therefore, FIT is the new frequency, FC is the original frequency. So the difference between FIT and the original carrier frequency, This difference is called as frequency deviation. How much amount of change has occurred in the new frequency with respect to the carrier frequency, that is called as frequency deviation. So frequency deviation can be calculated in two ways, two formula. One is by taking the frequency of the FM, difference between the frequency of FM. Frequency of FM is FIT. Difference between the instantaneous frequency minus the carrier frequency will give us the frequency deviation. Or we could also use theoretically that the frequency deviation is nothing but kf into am. This is another formula. So two formula are there, kf into am, and your other formula is difference between FIT and FC. FIT is the instantaneous frequency, which is the output frequency of FM, and FC is the original carrier frequency. The change in FIT with respect to FC is called as frequency deviation del F. So this is all we have studied now, and then there are different FM modulators and FM demodulators. That is, your FM modulators are the direct method, indirect method. FM demodulators are your PLLS FM detector, slope detector, and zero crossing detector. So this is what we have discussed. I hope it is clear to all, everybody. So let us now proceed. It's already 1 hour. It's already 5 o'clock. Okay, now I request Madam to share the video of FM. Madam, you have the video, na?
Yes, ma'am.
Okay. That is a very short, I think 2-3 minutes video. Then we'll start with the octave. So I'm just stopping the share.
Allow me.
I've allowed, madam.
Yes.
Madam, audio is not there. Sound?
Ma'am, now it came.
That signal across this
Now it is there.
of frequency modulated signal and demodulated signal. But that we will use this frequency modulation and demodulation trainer kit. In this trainer kit, just see in this circuit XR2206 IC is there. This will generate a very high frequency sinusoidal signal. The frequency is around 100 kilohertz. That is our carrier signal. We can get that signal across this FM output point. Without giving any message signal or sign input, we will take the carrier signal across this FM output point. After giving the message signal, we can get the modulated output, FM modulated output at the same point. First, we will take the carrier signal without giving the sign input. For that, we will connect the CRO probe positive terminal. This is our positive terminal. We have to connect with the FM output point. Now, you can see the carrier signal in the CRO. Then we will measure the frequency and amplitude of the carrier signal and trace. Then we will connect the message signal that we will get from the function generator. That message signal should be sinusoidal, frequency should be 1 kilohertz. That we have to set from the function generator. For that, we have to connect both the positive terminal of CRO and function generator and both the negative terminal of CRO and function generator. Then positive terminal we have to connect at the sign input. Then according to the patching connection, we have to connect the circuit. This is our patching connection. According to this patching connection, we will connect the circuit. Now, across this FM modulated output, FM output point, we will get the FM modulated output. This is our FM modulated output. We have to trace it. You can take this, other take this. Now you have to take the frequency. To trace it, and you have to take two time divisions, that is T1 and T2. Then you can get the F1 and F2. Then we will calculate the modulation index. Here modulation index will be always greater than 1. Then we will do the demodulation. In the demodulation, the input is the FM modulated output. FM modulated output is the input of the FM demodulator circuit. Then across this here you will get the demodulated output. So this is our demodulated output, whose frequency will be 1 kilohertz. That will be same with the message signal frequency. And amplitude may be less. Amplitude is around some millivolt range, but frequency should be same with the message signal. This is our demodulated output.
Okay. Okay, thank you, madam. Professor Sumit, will you take over now for the
Yes, ma'am.
octave? Uh,
Okay, ma'am, the screen is visible?
yes, visible. Yeah.
Okay. Okay, students, everyone, please look at the portal which I am saving. This is Octave program. So I have written this entire program. We are going to discuss step by step each of the portions. Okay. At the same time, I want all of you to learn some good practices about programming as well. Okay. In the first class, I did not go into much detail about this, but today, just looking at the program, you must have been seeing some additional lines and some additional colors here in the program itself. So these are some good practices we are going to discuss. Okay. So let's start. First, three commands I told you to write in all the programs to ensure that no other program is using those sort of constant and other variables which you are going to use. So this ensures that all A to Z and everything is available to you for this specific program. And then we will start as usual. We will define the time. Okay, we will define the time. The time key is defined between 0 to 1, and the step it is taking is 0.0001. Okay, so it means zero point 0.1 millisecond is the minimum time at which we are going to actually check all the data. So T, ultimately T is a, let me just double click here and show you. So this is the T. T is a 1 cross 10,001 long matrix. That means total 1001 points are there in between 0 and 1. Okay, this is we are doing for better accuracy. I asked all of you to play around with these values and look at the effect this has on the results. I hope some of you have done it, and I will discuss it. If you have done it, then we will discuss the results later on. Okay, so this is the first part, which is very, very common to what we have done in the last class. Next, we will start about message signals. So here you see this percentage mark, wherever in Octave or in MATLAB, this percentage mark is for the reference of the program writer. So you can utilize it to give a specific message to yourself so that you can understand this program later on. Or if you're sending this program to someone else, like if you're sending this program for evaluation to us, then we can also know that the following lines, these are concentrated at generating the message signal. So something like this percentage sign you can utilize to give information to yourself and to others for future references. Okay, so this means that now we are going to generate message signal. FM, the first step is also very similar. I have done some tweaking. Those tweaking I will try to point out. First thing first, let's define the message signal frequency. We have taken message signal frequency as 10 hertz. Then comes the definition of it. Madam has in detail discussed this part again and again. So I'm not going to go into much detail about this. The formula is cos 2 pi fmt. So that is what I have written directly. Okay. And now comes the subplot. Total, I want 4 plots. First one to be message signal, second to be carrier signal, third to be FM modulated signal, and fourth to be demodulated signal. That's why four. Total 4 plots in one column. This is the first plot. The last entry is saying that this is the first plot. What is the first plot? The first plot is the message signal plot. In the previous class, we have done till this point only. Now, I am adding some nuances to our graph. We know that the x-axis is time. So, we are now defining the x level. That this is the command we are going to use now. Okay, so x level, and then we also know that the y is amplitude. So we are going to use the amplitude as y level, and the title also we are going to use. The title means what is the title of this entire graph? The title of this graph should be message signal. And I want all of you to look at to this one, legend. Now we are going to include the legend. Legend is going to be one important factor through which we all, that means me and madam, we are going to identify that whether you have done this program on your own or not. This is going to be one of the markers. So you are going to create legend for all your graphs. And in legend, here I have written SD, the initials of my name. Instead of this, you are going to write your roll number so that we will know that at least you have gone into detail and at least you have put on the legend as your roll number. Okay, so always from now onwards, if you are producing any graph, make sure that you give this legend and then in bracket you're going to write your roll number. And here I am keeping the grid on. Grid on and off, we will discuss later on that what is the effect of this. Okay, so this is the going to be the process for any graph plotting. Define the signal and then plot it using all the details. Okay, so the same thing which we did for message signal, we are going to repeat for carrier signal. Okay, again we define the carrier frequency. This is the formula cos 2 pi fct, and this is the plot number 2 among the 4 plots. Time, amplitude, it is going to be the same. The heading will change. The heading is now carrier signal. And then again the grid on. Let me just copy paste this and demo to you that what is the output look like at this point. At this point, what we have done, we have only generated the message signal and carrier signal. Let's run it. Okay, so I hope all of you are able to see. So here, message signal, the title, the entire 10 hertz signal as message signal. You see now this graph looks complete. It is well defined, the time and the different time in between things and the amplitude, everything is properly defined. At the corner, at the right top corner of each graph, see what is there. It is written the line color along with the legend SD. I placed my initials as the legend. Instead of this, what you are going to produce in each corner of the graph, there should be your roll number. Okay, so this will identify that you have done this programming on your own. Okay, some additional things you can do: time in bracket seconds, amplitude in bracket volts or millivolts. You can add that for even more detail. Okay, so remember this, and the grid on and off. You see in the graph in between the light gray lines, the horizontal and vertical, they are the grids. If I keep the grid instead of on, if I keep it off instead of on, let's keep off and then run it. It will just do one thing. The results are not going to be affected. Only the grids are now not visible. In the second one, the grids are still on, but in the first one, they are off. But since they are like sinusoidal monotonic signals, that means sometimes grids are going to help you out in terms of understanding and calculating. Okay, so that is why I have kept grid on for all the graphs. Okay, so now I think before we go further, I think the timing is going to go off. Madam, ma'am,
Professor Sumit.
ma'am, if we can just restart so that I can complete the entire thing, the next part in one go, then that will be better. Let's
Okay.
stop. Okay.
Okay, so I'm ending the session. All of you should join again, all the students. Professor Sumit, can you record from your side? Your lecture. Can you record?
Let me try, ma'am.
Because when I am recording, no, then when I end the session, it takes time to load. In Zoom, it is not loading like in Google Meet. It takes time to
Okay,
load.
ma'am. Okay, then I am recording from my end.
If you see, if at least 1 or 2 classes, we should have the recording just for the sample.
Yes, ma'am. So it is asking the host to give permission to record.
Oh, so I should click the record button here.
This
I
meeting
don't know,
is being recorded. The recording has stopped.
Yes, ma'am.
Oh,
Hello?
okay. So I'll.
This meeting is being recorded.
No, ma'am. This is some sort of permission. I think we need to work on this. Then only it will be done.
So means what am I supposed to do for recording?
I also don't know, ma'am. I think till now I was thinking that only host can record.
Okay. Oh, so I can only record, but I'm recording, but whenever this session ends, no, and then it takes time. Slowly, it gets loaded. In Zoom, recording is a little difficult.
Yes,
Okay. Anyway, what we can not today, let us not record. One day we will do a meeting in Google Meet, and that class we can record. Google Meet, it's simpler to record. Huh? So just for
Otherwise,
example.
I can initiate the meeting and then record on my end. Whatever is better for you.
That is another option. Yeah. Next class you host from your side and see if you can record from your side.
Okay.
Okay. So I'm stopping the recording.
The recording has stopped.
Okay.
Yes. Okay, everyone. So now concentrate here. Till this point, if you have attended the last class, then nothing should surprise you. We have only added some nuances to the graphs which we are generating. Okay. Now let's move on to the main part, which is the FM modulation. So you just heard the entire detailed lecture what Madam has said. So in that, there was one important factor which was modulation index. Okay, so instead of defining modulation index in bits and pieces, that means kf multiplied by am divided by fm, what I have done, we actually made it one single constant mi. Okay, modulation index, or you can put b as beta. Okay, whatever is good with you. And here again, see the use of percentage mark. Here you I'm using the percentage mark just beside the statement to make a note that this mi is what it is, modulation index. So this is actually helpful. So make sure that you get into habit of this kind of thing. After even 1 year, if you will open this sort of programming, it will be very very clear to you that what is mi, what you have done. All those things will be really clear to you. Okay, so make a habit of these things. Now I have defined a modulation index, and I'm putting modulation index as 10. So we are going for wideband FM. And then comes the formula. This is the formula for FM modulation. If you have listened to the detailed discussion which Madam did, then it should make direct sense. Cos 2 pi fct plus beta sine 2 pi fmt. This is what we actually generated, and that is what I have written. The brackets and other things, it might confuse you right now, but once you start programming, you just need to keep a check that whether all the brackets are closed properly or not. Okay, otherwise you will get one error. Okay, so I just dictated the entire formula here, and then I will start my plotting. So now immediately I will start my plotting. For plotting, again, exactly the same thing. And here, what are we plotting? We are plotting S, that means modulated frequency, modulated signal. Let me just copy this here and paste it here. Let's run these first three steps. Look at the result here. I hope all of you are able to look at the results. First two steps, message signal, carrier signal, we already did. This is the third step which we just did. We wrote a formula for FM signal and then we are plotting it. Now here you can see the detail in which this FM signal has captured the amplitude variation in terms of frequency variation. When the amplitude of message signal is high, the frequency is high. When it is going lower, it is also going lower. The frequency is lower. Keep in mind, again, as Madam has said, in the FM signal, the message signal is not embedded in the amplitude of the signal. You see, the amplitude of this signal, if you just concentrate on the peaks or dips, it is a straight line. So there is no variation at all. Where is the variation? The variation is in the frequency. When the amplitude is high, the frequency is high. When the amplitude is low, the frequency is low. So that means we have generated a perfect FM signal, which is encapsulating the message signal in terms of the frequency, instantaneous frequency. Okay, I hope this is making sense to you. Now, now let's go back to our programming and go to the last part of this. Okay, so now here I have written FM demodulation. This is the last block where I'm going to demodulate it. So Madam have actually explained you two types of demodulation technique. In this one, we are going to use the second one, the differentiator with envelope detector one. And this first statement, what was the first thing we are supposed to do? We are supposed to differentiate the signal. Okay. And then this is the actual formula for differentiating. X is encapsulating all the differentiation of signal S. S is what? S is the actual FM signal. So the differentiated signal is captured in this X. Okay. Now the value, the absolute value will be stored in Y. So this is the Y we are looking for. Okay. You remember the explanation of Madam, then this should make the exact sense to you. After this, now we are able to actually transform the FM into AM. Now we just have to let it through a low pass filter, a Butterworth filter. So this part again, we are back to the AM demodulation technique. We have defined a low pass filter, which is a Butterworth filter, and these are the numbers which we are going to look for: 10 and 0.02. The better the filter, the better the output will be. Remember, I will try to show it to you during the course of the result. But remember, the better the filter, the better the result. Now, after defining the low pass filter, I'm going to apply this low pass filter. Here is the low pass filter. Where I have to apply? I have to apply it to the Y. So I have applied this filter to the absolute values generated here, and it will generate the final output as Z. So Z is the demodulated signal, and then we have actually plotted it. Okay. So here, let me show you the result, and then I will try to tell you that what is the one single thing we are missing actually. Okay. So let me just run this entire thing. I hope this part I don't need to explain. This is the fourth plot. I am plotting the Z, the demodulated FM signal, X level, Y level, title, legend, grid on. Everything is very well understood. Now let me run this entire program. Let me share the result. Yes. So this is the result. The first three graphs, they are exactly the same as we discussed earlier. And the last graph is the one which is showing the demodulated message signal. Okay. So now let me go and ask some of you. Asutosh, can you hear me? Asutosh?
Yes, sir.
So can you look at the last plot specifically and then point out any anomaly which this plot has?
Sir, amplitude has changed, sir. It has reduced.
It has reduced. And what else? What about the shape?
Shape somewhat has been restored, sir. Same is somewhat same as of the message signal.
But there are some minute altercation in between, right?
Yes, sir. In between. Yes,
Okay.
sir.
And anything else? Do you find anything odd in the x-axis as compared to the other graphs?
Uh, Sir,
Okay.
time, magnitude of time, I can see lots of change in that, sir.
Okay. Let me go to someone else. Joydeep, roll number 28.
Yes, sir.
Can you find anything different in the x-axis of the last graph?
So the time frame has changed.
What is the change?
Sir, in the first graph or the other graphs, it is from 0 to 1 seconds, 1 second. But in the demodulated message signal graph, it's from 0 to 10,000 seconds.
Okay.
The graph
Good.
is reading from 0 to 10,000.
Okay, so good. So we have found out two problems with our graph. Okay, so now let me address the first part. The first part is that the message signal and the demodulated message signal, they are not looking very same exact. So there are some in between anomalies or some small fluctuations, and the amplitude has also is also not same as the message signal. Okay. So now, if you remember the demo which Madam has shown just few minutes ago, the video demo, then you would notice that even in experimental or practical situation, the demodulated signal is not necessarily exact replica of message signal. So if you remember in the video demo also, the message signal was perfect sinusoidal signal, whereas the demodulated message signal has some sort of altercation. It was some sort of triangular or some sawtooth, something is there. Okay. So now here the importance of filter comes out. The demodulator requires a very good filter and then amplifier. So filter will make sure that the shape is very good, and the amplifier will make sure that the amplitude is what we are looking for. Okay, so there comes the importance of designing your good Butterworth filter. So now after this, I'm going to change some of the values of the Butterworth filter and let you know that what is the change which is taking place. So then you will be able to understand that filter is very important. The second thing is, let me just stop sharing this. And second thing is actually a coding problem. Okay, so remember this. The second problem is, instead of 0.2, 0.4, 0.6, 0.8 second. Here I am looking at 2000 points, 4000 points. It is not in seconds, it is something else. Okay, so this is the second problem. So the second one is coding problem. So here, now we are here. So if you want a better or worse output in terms of the presentation, then you have to play around with these two values. Okay, so I'm not going to do much about this in this class. It is up to you to play around and get a better or worse result. You can change it and see that how your result improves or it gets very bad by playing these two values. Okay, so this is the first point. Now, the second point I was trying to make. So here, this is the plot statement which we have used for plotting the last FMD modulated signal. Okay, plot Z. Whereas in other cases, we were plotting plot T, comma S. That means X is T. You're plotting the signal with respect to the time T. Here we have not done it. So let's try to do it. It will prompt one error. So what I am trying to do, I'm just trying to repeat. I'm trying to plot the demodulated signal with the with respect to time t. What will happen? Let me just simulate it. So what it is showing, let me just tell you that it is not showing the last result. For that, we have to go back to the command prompt. I hope the command prompt is visible. In command prompt, it is shown, it is written that the vector length must match. That means the t and z, they are not of same length. Now we will go to the workspace. Here, all the different variables and their length is written. Okay. So here, what is T and what is Z? Let's concentrate on that. Okay. So let me just close this and I will go to T. T is what? T is a variable which is 1 cross 10,001. So 10,001 elements are there in time T. And what about Z? X, Y, Z. All these have 10,000 components. So there is a mismatch. Okay. So one element is extra in the matrix T. Why is that? Because this diff formula is actually reducing the element. Okay. It actually gives us a lesser element in X. To rectify that, what I'm going to do, I am going to add one initial zero in this X. Okay. So now what it is doing, it is increasing the total number of elements and matching it with the T. Okay. So remember, you are going to get an error if you will try to just simply plot this T and Z because there is element mismatch. Whereas by just including one extra element and making it equals to zero, now you are actually making it equal. Now I hope that this should run properly. Again, I am simulating. Now let me show you the result. Okay, now everyone look at the result. Now all the results are proper and they are very, very similar to each other. Okay, the last graph which was previously showing the elements, now it is also showing the exact timing. Okay, so now the comparison between message signal and downloaded message signal is very, very easy. You can minutely check that the peak has slightly shifted, the amplitude is not there. For that, these grid lines are going to help you out. Okay, just for last example, let me just give you a demo about the change which will happen just by changing the filter slightly. Okay, so remember this graph. Okay, so the shape is more or less all right, it is sinusoidal, but there are some intermediate fluctuations. So let me go back and change the filter. Okay, so here is the filter 10 comma 0.02. Instead of this, let me go to 0.1. Okay, remember that number was 0.02. Here, now we are going to zero point 0.1. Let me repeat the simulation and show you the results. So here, see, the first three are exactly same because we did not change anything about the first three graphs. But the thing which we changed was in the last graph. Instead of 0.02, we placed a value of zero point 0.1. So here, this graph is also, if you look in one perspective, it is actually showing you the message signal, but the FC part has not been filtered out properly. Now the fluctuations are too much. Okay, so that is why I told you that the filtration is very, very important. If you tune it properly, then only you will get the result what you want. Okay, so this is all I wanted to show. Now, madam,
Yeah, Professor Sumit.
yes, ma'am. Do we need to like ask them to perform it right here, right now, or what should we do?
Let them perform for some time.
Yes,
We can.
yes,
This is
ma'am.
a small program. At least first
Yes,
part
ma'am.
they should write and show it to us by, I
Yes,
think, by maybe after 10 minutes, 10-15 minutes. 10 minutes we can leave.
yes, ma'am.
Let
Perfect.
some of them. Let us
So,
see
ma'am,
whether
let
some
me
of
just share
them.
the screen and for their reference, they can utilize it and then
Hmm.
try it on their own. So, I am just concentrating. I am not showing you the first two parts, message and carrier, but at least the last two part I am showing so that you will have a good idea. Now, everyone, you go back to your Octave panel and there you start writing this code. Right now, if you want to avoid the labeling and legend and grid, you can avoid it. But if you can do it, then that will be best. Okay, so start programming. We will start checking the results, or if there is any error, then we will start checking after 10 minutes. Everyone,
So could
start
you scroll
programming.
up for a second?
Okay, to the top,
Yes, sir. Yes, sir. Okay, sir.
done. Okay, I think the first part, as soon as you write it, I think more or less just by copying, pasting, and changing the things, you can do it. So this is the major part, the modulation and demodulation. Everyone start your programming. Don't think that just by copying pasting later on you can understand the concept. If you do it on your own, then we are going to rectify all the problems here right now. Everyone start programming.
Sir,
Anybody has any doubt?
ma'am, I'm not getting all the graphs, ma'am, after simulating it. But after running the program, ma'am. So I want to share my screen. Can I?
As soon as someone is done, please share your results with us. Or if you're having any problem, let us know.
He's having some problem. Now you can share your screen. Show it on the screen.
No. Sir, this is the program, sir, but I'm not getting the graphs and results, sir. So I'm running it, sir. Sir, this is the error coming in, sir.
Remember the value for Butterworth, which I have optimized, is 10 and 0.02. Okay, so stick with this one, and then if you want to see the variation result, you can do it later on. Right now, stick to 10 and 0.02.
But are we able to see his screen? I'm not able to see his screen. Where is his screen?
Yes.
This is. Huh?
No, ma'am. It's not visible, I think.
So you share your screen, na?
Number one, do you want to share the result?
Yes, sir. Wait, sir. Sir, the result is not coming, sir. Actually, the graph is not appearing, sir. Once it appeared, and after that, it's not appearing when I'm rerunning it, sir.
Yes, roll number one. What was the problem?
Yes, sir.
Sorry, I was not able
Sir,
to hear you.
Okay, sir. I was not getting the desired output, sir. In fact, I was not getting any output.
Can you show me the program once again?
Okay, sir. Sir, do I need to load the package?
Yes.
Because I have not loaded it.
Yes, you have to load it. So everyone,
Okay,
this
so every
one,
time, sir.
yes. Again, we are going to use those package formulas, package codes. So everyone, please load in your command prompt the signal package which you have downloaded last time. EKG space load space signal. That is the command which we used to load the signal package. So without that, this program will not work. Asutosh, mute yourself, do the rectification, and then show us the result, okay?
Okay, sir.
Anyone else who got the result, please share screen. Arijit?
Sir, I received it.
Okay, 17, please share screen.
Okay, sir. Sure, sir. Sir, is my screen visible?
Yes.
Sir, I
Perfect.
received it.
So now what you want to do, roll number 17, try to
Yes,
check
sir.
once if you change the value of beta, the modulation index, what
Yes,
will
sir.
happen? Will increase or decrease it. And once you find out the thing, the concept which madam explained, if you can correlate it, then let me know. Okay.
Okay,
So
sir.
right
Okay,
now
sir.
we
Sure.
have mi equals to 10. What will happen? You change it to, let's say, 1. What will happen?
Sir.
Try to look at the result and then let me know. Okay. Stop
Okay, sir.
sharing.
Sure. Yes, sir. Absolutely, sir.
Anyone else?
Professor Sumit, we need to tell them about the writing of record also, no? For next class, they will write the record.
Yes, ma'am. Yes, ma'am. Yes, ma'am. We can start explaining that, and then if someone will have results to show at the end, we can check one or two results and then end the class.
Because that will be better.
Yes, ma'am.
So what? So you will share the screen from you have the format. Now should I share it?
Yes, ma'am. If you can do it, then that will be better.
Okay, so let me open it then.
Sir, please share the format in the Google Classroom also, sir.
Yes, yes, we will share it. Don't worry. So remember, student, Madam is going to explain the format, what needs to be done, and then it will be shared in the Google Classroom. And you're going to look at this format and submit all the records in this exact format. Okay. And the graphs and modification, what I have told you in this class, they apply to the graphs of the previous experiment as well. So experiment number 1, the graphs should have all the titles and the legends and everything. Okay. And I told you, if you want to be more specific, then you can go for time in bracket seconds, amplitude in bracket volts, all those things, minute thing you can do on your own.
Okay, so this screen is visible.
Yes, ma'am, it is.
Okay. Okay, students, so just have a look at the format. So this is a common format for C lab. All these C groups, communication engineering groups, they have to write in the same format. So the first page you can see should be of this form, or with the logo and everything. Whatever is there in the format, in this exactly same manner, you have to write your record. So first page with the logo and all these things, whatever is present there, School of Electronics Engineering, Communication Engineering Laboratory, then experiment number you have to write. Then after that, your name, it is all self-explanatory. All these pages are self-explanatory. You can see you have to make this kind of a column. Name, write your name should be typed, roll number should be typed, branch should be typed, and your semester 5th or 6th, whatever 5th semester, you have to type it. So that this is page number 1. Just a minute, battery. Let me connect the power. Okay. Then next page. So this is page number 1. In page number 2, you see what is the format given. Next after the page number 1, you should write down the aim of the experiment as per the lesson plan. It should be handwritten. So please read the instructions carefully. These are all written in detail, all the instructions. I don't even need to explain so much. I'm just quickly just telling you aim of the experiment as per the lesson plan. It should be handwritten. Write on sheets of paper, preferably blank sheets without lines. Scan and paste. Okay. Then next part will be software required. So what software you're using? JNU software, Tina. If you have performed the experiment using Tina, then you'd mention about Tina also along with Octave. And all these things you have to write from Texas Instrument, whatever must be handwritten. Everything is handwritten. So aim of the experiment, software required, then theory. Briefly mention the theory. So in brief, you have to write the theory about the experiment, write the definition, draw the block diagram, write some basic equation. That's all about the theory. And if I'll be sharing the manual, but you should not be copying and pasting each and every word from the manual. That is only for the reference. You should write the theory on your own. You already have notes in your theory last semester. So try to write something different from the manual. Your structure, your basic thing should be same, but write it in your own words. Don't write word by word from the manual. That is only for your reference. Hmm.
Yes, ma'am. Yes.
Then theory. Then after theory, you have to write the procedure. Procedure followed for the simulation. So only the simulation procedure you have to write here, not the other. Otherwise, the other thing is video demonstration. In video demonstration, you are doing nothing. You're just seeing the video. So the procedure has to be written for the simulation. Again, it is handwritten. Make a flow chart or the process flow chart of it, whatever process you have used in the simulation of what all the experiment AM, DSPSC, SSBSC, and today you are doing FM. So make a flow chart and see all these things are written here. In AM, first process signal generation, then modulation. So this kind of flow chart you're going to make. Evaluation of modulation index, trace the graph. So everything is written here. Read it and follow the instruction. The next is program or JNU radio block set that you are going to write here, the programming part. And program for generating some signals are here. The name, roll number, you have to write. Take the snippet, example code snippet. So read the instruction, it is there. So here like this. This is how you are writing, no? Clear, all that you have to write down. Then observations, if there are there, see, must be handwritten. Paste the screen. Observation means paste the screenshot of figure obtained from simulation, all the graph and all. Roll number must be present in the title of the figure. Whatever simulation you have done in the graph, just now sir has told you, no, legend, that legend part, your name, the roll number should be there in the graph, and you paste it. And whether waveform were seen or all that, write the observation. No, observation means once you have taken the graph, then you write something about it, like you did what did you observe in the graph. If you have generated AM signal, then what is the graph telling you? For M less than 1, for M greater than 1, for M equal to 1, what are the things you understood from the graph? That you have to write few lines. And even the demodulation, how did you know that demodulated signal is same as the modulating signal? Write few lines about it. So such type of observation you're going to write along with the graph.
Screenshots will be pasted in the observation section, right?
Yes.
Okay.
Of the graph. Then modified task, if there are any modified tasks, if there, then you write about the modified task. Otherwise, you can leave it. And then here, generate a modified task, like generate AM waveform with percentage given. Suppose the last 2 digit of your roll number, if you have generated AM waveform with the last 2 digit of your roll number and you have generated some waveform out of it, that would be your modified task. So do some kind of modification also and paste it along with the regular AM waveform that you have generated. You have to do some little bit of modification in the values and get a graph out of it and paste it and write the topic modified task. So what are the type of modifications you can do? These are the examples given in the your format. And in experiment 2, what kind of modification you can do? This is the generate FM signal again with some last digit divided by 10, something, some value you change and get a graph out of it and write little bit of observation. That is your modified task. And finally, the conclusion, it must be handwritten. And lastly, submitted by your name, roll number, and branch, and sign on each end of each page. So this is the format you have to follow. So I'll be sharing it in your Google Classroom. All of you should write and submit the first 2 experiments, isn't it? The first experiment and today's experiment, both submit together. Professor Sumit, what time and date should we give them for submission?
Yes, ma'am. By Saturday night.
Saturday night.
Yes, ma'am.
Okay, Sunday. Today is Monday, no? 4-5 days are enough to write. Yeah.
Yes.
So,
yes, ma'am.
so
Just something, ma'am. So,
yes.
In observation part, everyone please understand, as some students suggested that, yes, you need to plot, you need to screenshot or add the image files in that specific area, but at the same time, observation does not merely mean results. It also means that what did you understand from that result. So after those results pasted from the output, you also need to explain that the observation, yes, it is as per our, you need to discuss it a little bit more. And the last thing, madam, and students, the modified task for first two experiment, it is already written. For experiment number 1, all of you have to do these 3 modified tasks. Okay, along with the main experiment, you have to do modified tasks as given in the list. And for experiment number 2 is also listed in this one. And the upcoming thing, either we will let you know, and then you are going to do those modified tasks as well. Okay, so for first 2 experiments, it is already written there. For upcoming experiments, we will let you know the simple modification which you need to do and add in this section, modified task section.
Okay.
Excuse me, ma'am.
Yes, one by one.
Quickly,
Number 20.
Yes, ma'am.
Sir,
Yes, ma'am.
could we
Ma'am,
have
in
some
the
more time because there are 2 experiments and these are very long. So, and we have other labs also. Could we have some more time?
No, but your next experiment will be, third experiment will be on Monday, no? So before that, at least you have to submit 2 of them, no? Again, it will accumulate. With experiment 3, it is going, 2 more will be accumulated. So you should finish by Sunday, at least Sunday night. Sunday
Yes.
by 12, you finish
okay,
it off.
ma'am.
Okay?
Yes, Sunday is better.
Sunday 12 o'clock, because Monday again you will have third experiment. So before that you update yourself. No, Sunday night you upload. I'll give the time till Sunday night. Okay, all of you.
And
So I think